Alright, this is number 13 as we can see. Another complex problem. These things can be pretty confusing. Roots of unity again. If we're going to let w be cos 2 pi over 5 plus I sine 2 pi over 5, and we're going to show that w, that number, or yeah, the complex number given, is a root of the equation, then we can just take it and use De Moivre's here. So, where's my pen? There. We're going to take it and we're going to bring cos 2 pi over 5 plus I sine 2 pi over 5, and we're going to try to show that this thing to the power of 5 minus 1 is 0. Excellent. Well, we know that by De Moivre's the r value is 1, so the fifth root of 1 is just 1, that's not a problem. Then let's bring 5 in front of each of these. So now you have cos 5 2 pi over 5 plus I sine 5 2 pi over 5, and minus 1 equals 0. Now a really nice thing happens here. The first part of this problem is pretty easy. 5's cancel, 5's cancel. We have a nice situation here where you have cos 2 pi plus I sine 2 pi. We want to show that this minus 1 is 0. Well, from our special triangles, we know that this is 0. And cos of 2 pi is 1, and that's obvious that 0 is 0. Getting our first 3 marks. Okay, this part's a little bit more interesting, and then C is, again, takes it one step further. So we need to show that this times this is this, and then deduce this thing. Well, again, that's not too hard. It's already laid out for us. It's a show problem, so we have to show the steps. We have to show this multiplying each of these, and then we collect like terms. So actually there's nothing very difficult here. W to the power 5 plus W to the power 4 plus W3 plus W squared plus W, and then we're going to subtract W4, subtract W3, subtract W2, subtract W. 1, 2, 3, 4, 5, 6, 7, 8, 9. What did I forget? Yeah, subtract 1. Good. And collecting like terms, those are going to disappear. W3s are going to disappear. W squareds are going to disappear. W's are going to disappear, and easy enough, we get this, which is what we want. So if this works, then therefore, this thing has got to equal 0, because 0 times anything is 0, 0 times anything is 0. Sorry, never mind that last statement. Okay, so they expand, which means that once they come to the same thing, this is a factor of this, and this must also be a factor of that. Good. Now comes the tricky part. And due to my handwriting, I'm actually just going to explain the parts of the mark scheme rather than write it all out again. Okay, so here is the problem for 6 points. Hence is the big key word here. Hence always means use the result above. Okay? Show that this is a true statement. Well, let's just start working and see what happens. It's a hence, so we know how to get started. We're going to have to use this. And in part A, we're given some information. So let's start with that. 1 plus cos 2 pi 5 plus I sine pi 2 sine 2 pi over 5. This comes from when this is 0, right? And then we put in 1, 2, 3, 4, right? The different powers from what we know about roots of unity. So we know that there are going to be 5 of them. All right, so that's the first statement. Now, like we did before, we're going to take these powers and put them in front of the angles. Oops, that's not what we want. And start simplifying. All right. So 1 plus cos 2 pi over 5. And the 2 comes in front. We get cos 4 pi over 5. I sine 4 pi over 5. That's going to become a 6. 3 times 2 is 6. 4 times 2 is 8. All right. This next step is probably where some of you got lost. Up until then, it's pretty straightforward. It's hence, so you can pick these points up because it's telling you what it wants. Let's leave this the same. All right? But then think about our goal. And then we're going to play with this side. How do we get from here to here? Okay? Let's take this angle, 6 pi over 5. That's this angle here. Right? 5 pi over 5 plus pi over 5. Right? Now, that is the same as, let's put our positive and negative quadrants. Oops. Okay. So here, cosine is positive. 6 pi over 5. Sorry, cosine is negative. Here's the other place that we have the same value. And that has reference angle pi over 5. So it's 4 pi over 5, sorry. Okay, so that's what explains this step here. Then sine 6 pi over 5. Again, sine over here is negative. Once you move to this quadrant, to 4 pi over 5, then sine became, it switched value. So if it was negative, it was positive. It's positive, so it becomes negative. That explains this sign change here. Okay, so something similar happens over here, where thinking about the quadrants, but now 8 pi over 5. 8 pi over 5 is down here, which leaves a reference angle of 2 pi over 5. Okay, this is where cosine is positive. If we want this, the same value, cos is going to have the same sign. So cos of 2 pi over 5. And here, cos was positive, and all were positive. But we're interested in sine, and sine changes signs as you move between those two places, so it's minus. Okay? That's the trickiest part. Why do we do that? Well, we can from all our knowledge of the trig and circular functions unit. And here, because this is our goal, that's what we're trying to show. All right? So then, the 1 is obviously the 1. Cos 2 pi over 5, and cos 2 pi over 5 is 2 cos 2 pi over 5. I sine 2 pi over 5, and I sine 2 pi over 5 disappear. Cos 4 pi over 5, and another one gives 2 cos 4 pi over 5s. And these are going to cancel, which leaves us with this statement. Moving down, we then subtract 1 from both sides, divide by 2, and suddenly we are finished.